All right, thanks everybody. We're going to go ahead and get started on the second part of the presentations. So we have a total of 10, I think. So we're going to get through these pretty quickly. So I'm going to go ahead and start, and then we'll work our way around the room. Probably need to mute this. So, I'm sorry, Stu's going to start. I'm spacing out here. Go ahead, Stu.
Okay, either way, let me share a screen here, Stephen, and some sound as well, if it'll work.
Just make sure to check the sound box when you share.
Really?
I believe so.
Okay, I have a couple of different things I wanted to share with you regarding the effort that I've been putting in lately on getting new educational material put together. So, following Stephen's lead on the W0TLM website, I decided to overhaul my ham radio school website, and that's what you're seeing here is the homepage for ham radio school, and that is what the material that we use for our education courses and the ones that we'll use in the fall for the fall classes. Um, and it was really incredibly easy, relatively speaking, to put this together compared with the last manual effort. So, like Stephen, I was using the Claude AI system to make updates and changes to the website, and it's a pretty big improvement for me. So I'm very pleased with it. But one of the features that I added is what I'm calling visualization apps. And these are utilized by instructors, and they're also in the course videos that we use for the new technician license course. You may be aware that the technician question pool rolls over starting July 1st. And so I've been putting in a lot of time getting that new course spun up so that we have it ready to go, and that I can distribute it around the country, actually. But these apps are educational visualization apps. They're each of them performs or illustrates one concept essentially. So I'm going to launch one of them here, the AM simulator. This is amplitude modulation, and it's pretty simple, really. Down at the bottom here, I can make a wave, so I can adjust the frequency of the baseband up here, the audio, if you want to think of it that way, and the amplitude of that as well. And you can see the commensurate radio frequency change that comes with that amplitude change or that frequency change. I can then add additional components to that wave and make a more complex waveform and illustrate how that impacts the amplitude modulation. So that's just one of the examples. I've also have one for frequency modulation. I'll skip over showing you that one. One for CW just illustrates how CW is sent. I also have one for frequency shift keying. So if I put in here, if I type in some text, I'll type in, I don't know if you can see that on the screen or not, W0TLM meeting tonight. And right now I have a 4-tone FSK scenario selected. And if I start the send on the it sent it in 4 FSK, and I can zoom in on that and take a look at the binary digits that resulted from using 4 different tones to represent 0, 0, 0, 1, 1, 0, and 1, 1. And then these are encoded in ASCII. So here's the letter N, which is 0, 1, 1, 0, 1, 1, 1, 0. And you can also choose 2 FSK and switch it over to that. It shows you different frequencies being used and a stair step function. And you can also go to 16 FSK and depict it that way and send different messages. Or it's just good for illustrating frequency shift keying and how it works essentially. One of the ones I'm more proud of here that took a little more effort to get right is a QRM simulator, and I'm going to start the receive um, sound here in just a moment. But what we have here is two single sideband signals, essentially, and then what you see in kind of the red window here is the receive filters that an operator might implement. And I can change the position of these two signals relative to one another. So I can set up various interference scenarios, and I can also change the low cut and the high cut position of the filter that I want to apply. So it's really good for illustrating receive filters on sideband, or I can switch over to CW and illustrate the same thing with CW signals. So I'm going to give you a brief example. I've got some canned audio that this uses, and it's uh, it's pretty realistic. I'll put in some interference. If I take the high cut, I can get rid of some of that interference. So it's pretty much like operating on sideband. Very good. This, any individual who signs up for the course, or actually these are open, so any individual can go to our website and piddle around with these. Just kind of fiddle around with them and experiment and kind of get an intuitive understanding of how things work. We also have a time domain and frequency domain, fast Fourier transform analyzer. You can record your own audio and examine it in the time domain and the frequency domain with this app. I have a filter app here that illustrates different types of filters, band pass filters, low cut, high cut, of various sorts. You can also record your own audio here if you wish to filter it and play it back with various filter settings, or you can just implement a white noise or a sine wave or various combinations of things. And when it plays, you hear white noise. I can move the center frequency around, and hopefully you can hear the difference in the different filters I'm applying. So again, just illustrative of very good for illustrating to students how what effect filters will have in the audio domain, at least. We also have an SWR wave superposition simulator here that if I turn off, here's a forward wave and a transmission line. I can adjust the frequency of that and the amplitude of that. And then I can add a reflected wave. So if an antenna has an impedance mismatch, I get a reflected wave back down the transmission line. And of course, SWR is a comparison of how those two waves sum together. And that's illustrated with the black wave here. And I can adjust, the frequency and the amplitude of each of the forward and the reverse wave to see different effects. So the high voltage versus the minimum voltage here would be the SWR. That would be how you compute it, and it's computed and read out down here at the bottom of this particular app. Last one I'll show you here. We do have one for Ohm's law, one for a dipole SWR simulator. I'll show you that one real quick. So we've got a dipole antenna, and I can adjust the length of it, and it moves the SWR curve around the 20-meter band, which is kind of the shaded area on the bottom that you see here. And that one's pretty simple. I can also add loading to that. I can insert some inductive coils, and you can see the Q beginning to narrow up on the SWR curve with the loading added on the antenna. A more complex version of that for a vertical mobile screwdriver antenna This one's a little complex, but I can change the antenna is depicted over on the left. I can change the length of the antenna element. I can adjust the number of coils that are applied to that antenna. I can also adjust the position of the coils on the element, all of which affect the SWR. And so if I zoom out here, you can see we've got all of the HF bands indicated here, and I can move the SWR around by changing the loading. I can also apply a capacitive hat and also adjust the size of that capacitive hat, and it moves the SWR curve around a little bit. But again, very useful for illustrating antenna design factors and how they affect SWR and how you get an antenna tuned to a particular band when it is a physically short antenna like we're depicting here. When SWR goes above 2 to 1, you get recommendations for optimization on how you can fix that, how you can correct the antenna design that you've got, or you can just apply a tuner if you wish to do that. We've got some presets up here for each band. You can just click on that and it kind of optimizes for each of the HF bands and a design for you. And these are based on real world calculations. I believe it's called the Wheeler model, Wheeler single layer coil inductance formula. So they're mathematically correct. So pretty good estimates of real world antennas. So that's the apps. There's about 11 of these things. I invite you to visit Ham Radio School and look under the learning menu for visualization apps. And that's where you'll find these, and you can play around with them yourself. And if you've got feedback or ideas of more things that you might like to see, let me know about that. We'll be using these, like I said, in the fall class, and we use them in the video lessons that we have produced for the new technician class. And or speaking of that, how much am I out of time? Hans, Robert, either one of you?
Kinda.
You want me to shut up now?
Yeah, if you wouldn't mind wrapping up. We've got 10 presentations.
Okay.
Through.
I'll leave it there. That's what I've been working on. That's what I got. And I'll
Thanks,
stop
Stu.
the share now.
It looks great.
Let's see. How do I stop the share? Oh, there we go. Thanks.
Thanks. Stephen, if you could bring up my camera, my window. The one that says Robert Ray's iPhone. Okay. So I'm going to try to do this with both hands. Does that work? All right. Okay. It's working. So real quick.
Robert, if I may, before you do.
Yeah.
I think Jonathan has to do that for the room. I think I can only do it for the Zoom community. Unless you see your camera full screen right now.
We see my camera full screen.
Oh, then I might have gotten it. Okay. I just pinned it in case Jonathan's wondering.
Okay. It's not showing up on my phone, but I'm not.
Think of your TV monitor as a large viewfinder for your phone.
So it's showing what we're supposed to see.
Good. Okay.
I can't figure that part out. So, Stephen, the Zoom people aren't seeing my phone.
I've got it here. I just had to
Yeah, I've got it.
remove pins on if you've got somebody else showing up on your screen.
Yeah.
Okay.
Yeah. That's why I was suggesting that Jonathan do it, because it become the.
Okay. I think we got it. So what I'm showing right now is so I'll start with the little bit of background. I wanted to come up with a small kit I could take with me when traveling with minimal footprint and minimal setup. And so I found this. This is a ZBitX version 1. It is a kind of an all-in-one radio. It does CW single side band. Right now it's running FT8, and it is actually receiving. made a contact before we got started here, and it's just paired with a 20-meter telecraft antenna, telescoping antenna, and that's the sum total of it. There's a little tail on the end of this that, as Jonathan can attest to, helps with the SWR. So cool little radio. There's I can't show you all the aspects of it, but it is. Let's see if I can get zoom in there a bit. It'll go up to 5. So I was running it earlier. It was usually outputting about 3 watts. ZBitX version 2. This is part of the BitX community. Asher Farhan built this. There is a version 2 now that's got some improved firmware and all that. It's got some quirks. Probably one of the, as most of these things do, probably one of the biggest things, it gets very hot. So you really have to give it some additional cooling, which I'm working on, 3D printing in another enclosure. So that's the setup. It works pretty nice.
Okay. In 1997, Alinco was thinking we need to make a very, very, very small HT. And well, the text is not important. That is the radio. Very small. And because they wanted to make it very small, they did not put a speaker in it. So if you want to listen to it, you have to plug in either a hand mic or a headphone or Apple earphones. But that works, and it is both. It's VHF. It has air frequencies. It has weather frequencies, and it has an extensible antenna. Yeah, there you go. And it emits vastly less than the previous radio, about 1/3 of a watt. But it works. And let me plug in a big old speaker, mic. And there's the weather signal. Yeah. Here inside the room with this tiny little antenna. So they succeeded in making the smallest HT in 1997. However, you needed big stuff to make it work. Yeah. Okay, that was it for me.
Excellence.
Well, I think that, can you hear me?
Did you turn it on? No, it's on. Okay.
I think that, yeah. So I've got quite a few radios at home. I've got the NFT Yaesu radio, and I've got a ICOM radio, and I got 2 of the QRP radios that this gentleman is going to be demonstrating. And then I got a whole bunch of these guys. They're so cheap, they're easy to buy. And I bet some of you, I think I see one maybe over there. I bet some of you have these Bofang radios. If not, you've seen them. They're cheap. Can't go wrong with that. But the antenna is not very good. And so what I discovered was that this is the antenna that I use. And I use both every time I get on the net. But this antenna changes this very significantly so that it's actually a very good radio, and I can reach quite a ways. I've gotten all the way from Sedalia, west of Castle Rock, down here, and hit our area in Monument. I'm not talking about the repeater, but talking because I could hit the repeater too. That's what I use for all of our nets at night. And so that's really helpful. And so if you've got one of these, get this antenna. It's much better. And when you put that antenna on it, this becomes quite more powerful. This is I think it's called a Nagoe. It's an NA771. You can find it on Amazon, not very expensive. The other thing that I've discovered is that the battery life on this thing doesn't last very long. How many have one of these and have found the battery doesn't last long? Anybody in here? Nope, probably not. Well, it turns out, if you can just hold that for a second, it turns out if you upgrade this battery, and I've got one here, you just click this battery in here, and now this battery lasts a lot longer. And so you can you can go out, you can climb a 14er or something and reach out to people, and it really changes all of these radios into something that's much better. And so that's what
Only thing I'd add there is beware of counterfeit antennas. These are prone to counterfeit, so make sure you're getting it from a good source. Yeah, there's a lot of different ones out there. You really have to understand which ones are counterfeit or not. So, Stephen?
Yeah.
Yeah.
So about 70 years ago, um, when I got my novice license, I built um, a tube transmitter, and I had a tube receiver. And the tube transmitter was actually, I went around on trash day and found radios that in people's trash, and I rescued a transformer from an old TV set, and that was the high voltage transformer for the little 5 watt one tube radio that I built. 20 years later, after I was married and had a couple of children and full-time job and all that kind of stuff, I started getting interested, and I worked at HP where there was a lot of engineers, and I was an art major. So every time I built something and it didn't work, I had to go buy my friend's lunch, and before he'd turn on this expensive oscilloscope or spectrum analyzer and probe the circuit and say, there's your problem. Anyway, there was an article in QSC, I built this tiny little 200 milliwatt transmitter on 40 meters. And it's crystal controlled. And there was an article in QST W1FB, Doug DeMaw was his name. And so I saw this article and I thought, oh, that's cool. But it only puts out 200 milliwatts. That's a fifth of a watt. And so I thought it would be a real challenge to try and work, see how many states I could work. And I managed to make 30 contacts with it. And I put all 50 states on here, and you can see in red the states I've checked off. I've actually checked off 20 states confirmed running a fifth of a watt. Of course, I had an antenna at a wire that was probably 120 feet long, strung up in the trees between my house and my neighbor's house. He was an engineer that worked at HP, so he was very friendly to me draping wire across his property. But anyway, so that was 50 years ago, and now I've graduated to 5 watts, and the radio's a little bigger, and it does 5 bands. And oh, by the way, I did work Asia and Europe on this radio. It wasn't a very long conversation. And so this radio actually puts out 5 watts, which is, if my math is right, 25 times what this little flea-powered radio does. This radio ran on a 9-volt transistor radio battery. This radio runs on a 11.5-volt lithium cell. And this radio probably cost me $1 or $2 in terms of parts. I had access to lab stock, which made it very helpful. So that's my story.
Thanks, Steve.
Sure.
All right. If you wouldn't mind introducing yourself.
Oh,
I'm Pierre, W0PJG, and I didn't make anything myself, but I do watch YouTube, and this is something that I saw. It's before ATS mini radio, and I have it on an FM just to show that it has a speaker, but it has quite a few HF bands, and did I go the wrong way? So it'll actually give a message that it switches to single sideband and all that. But it's actually the second one I bought because the first one didn't work, and then I decided to try again a few months later. Yeah, loading single sideband there. But yeah, I thought it was kind of fun, and you can plug a a headphone into it or another speaker or something like that, and it does actually sound better when you do that. And it came with well, this antenna is just a FM, I guess, radio antenna, but it also came with this one. And I don't think the performance is all that good, but you see the frequency range on that one. So it's 9.9 kilohertz to 181 megahertz. Just to in case you can't see it. Anyway, I thought it was just kind of fun, and obviously 3D printed case and everything. And so if you buy one and it doesn't work, send it back and go with somebody else. I guess less. It was under $50.
Thank you. All right. You can introduce yourself.
Okay, Dick Barthel, K7RMB. I brought a couple of things tonight. This device, as soon as he gets his camera going. And I'll just describe it. It's a Morse code tutor that I built. There was a fellow by the name of Jack Perdum who actually, I think he presented a paper back in 2018 or 2019 at FDIM. And another fellow by the name of Bruce Hall was inspired by it. He kind of came up with some schematic diagrams and so forth. Anyway, I took it to heart and went ahead and built my own. But what this little device will do is simulate. I mean, it's actually a training device. And I'll just turn it on here. I set it to run it pretty fast, so it'll just do random words. And as it puts out the code, it spells them. But the idea is that you would be listening and, to verify what you're hearing and decoding yourself in your head. And then read it and then figure out the code. That's probably what usually happens. At any rate, it does receive, it does sending, has all kinds of configurations, but very helpful as far as it'll even actually simulate QSOs, so you can hear like just standard contact info back and forth. What it would sound like as you get used to it yourself. So, and that's that. And then the other thing, and you can also send on it. I got a paddle here. The other one is this little device. I didn't power it up or anything. This is like from QRP Labs. This is a very popular radio these days, but it's a 5-band transceiver, 5 watts, and it'll work sideband and it'll do, FT8, all the modes, except I don't think it does FM. But it's a very sensitive radio, and it's a kit. It's one that you build yourself. So for builders, it's very popular. So There you go.
Jonathan, okay.
Jonathan, AE0WO. I brought a couple of things today. First one is, I think a little tool that everyone should have that's the Nano VNA, and it can for a few bucks. It's really not that expensive. It can tell you all kinds of information about your antenna, like this antenna right here that came with the radio. I don't know if you can see that. It's about, I don't know, a couple inches long. Has an SWR about 3.5, so not great. So it can tell you some stuff about your antenna and if it's matched to your radio. The second thing I have here is a little project I was thinking about. You know, we have these HTs, and I was real happy with the FT991. You can just plug your radio into your computer, and you can do digital mode. You can do packet radio. Why can't you do that with an HT? Why don't they just put a couple little circuits in there? Would be fine, right? So I thought of what is the way you could set up and maybe get a whole station together pretty inexpensively with some common parts. So I thought, you know, you could take this radio here and tie it into a Raspberry Pi. You can get a little monitor on that, keyboard and a mouse. And with a small amount of circuitry, if you point over here to the circuit diagram, like a couple simple components really, you can build the interface to this radio, and you could do packet radio, type out a message in WinLink, send it off, get something back with this little handheld right here. And this was 18 bucks, so you know, it's cheap. I think you can get into packet radio fast. So, gonna package it up. First, I got to get the circuit to work though. That's the first challenge. Who's up next? LD. LD.
My name's LD, call sign Whiskey Zero X-Ray Lima Delta, and my show and tell is actually a hear and tell, maybe something like that, because it's about digital voice. If I say digital voice, everybody's favorite digital voice mode is. Wow, you got like 3 big ones to pick from, right? DMR, D-Star, Yaesu System Fusion, right? What's yours? DMR, okay. So my issue with the digital voice modes is that most of them are based on an audio compression algorithm that by licensing fees has to be implemented in like a hardware dongle or something like that. You have to pay to get that added to like your hotspots and stuff like that. And Yaesu System Fusion is just built for one purpose, and that's basically customer lock into one brand so they can sell more Yaesu radios. That's not particularly ham radio spirit in my opinion, but some people really love it. So that's been like the scene for the last 10, 20 years or something like that. But the open source community has been really, really busy over the last year, and they've implemented software called FreeDV. Anybody heard of that or used it yet? Okay, so FreeDV is a digital voice mode that is all open source. It uses a completely new compression algorithm. They've been working on a couple different compression algorithms over the years, but just in the last year, they've used machine learning to do really awesome voice compression algorithms. So what I'd like to play for you is a couple different voice samples. So if you're on Zoom, I encourage you to go to the freedv.org website and find the March update, because I don't know how well these audio samples are going to translate over Zoom here, but I want everybody to be able to listen carefully and hear differences between some of these audio codecs. So here's the input sample, and this is on the FreeDV website, so you can get like their input sample.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
If he sounds Australian, that's because he is Australian. Let me play that one more time. This is what it sounds like uncompressed before it goes through this voice codec.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
And if I say for a basis of comparison, let's listen to it when it's modulated as SSB. Probably everybody knows what that's going to sound like, right?
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
Okay, so everybody's familiar with that, what the single sideband sounds like. Sounds like an awful lot of degradation in there, right? Okay, so let's compare that with this. This is over the cable sample. Okay, so they aren't pushing it from antenna to antenna. They're just pushing it from an encoder to a decoder over a wire. All right. So this is what So the software is called FreeDV. The framing mechanism is basically the same for all codecs, but the name of the codec is RAID version 1. Here's what RAID version 1 sounds like. This is what they've been working hard on over the last year, these FreeDV developers. Listen carefully. Tell me what you think of this audio quality.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
Does that sound pretty good to anybody else? I think that's awesome, the quality that they have achieved over the past year. Here's the real kicker. This is awesome, awesome, awesome news. How much bandwidth, how much frequency bandwidth does human speech occupy typically? That's what they teach us for the test, right? 3K, that's wrong. I didn't say the human voice, I said human speech, and speech includes more than just your vocal cords. It includes your teeth and your tongue, S's and T's that don't involve your vocal cords. Okay, S's and T's have higher frequencies than just 3 kilohertz. So what they've done with this compression algorithm is they have used 6 kilohertz of input. Okay, so they're capturing 6 kilohertz worth of human speech instead of just 3 kilohertz. So that's why it sounds better in like the S's and T's. Let's listen to that one more time. Listen for your S's and T's.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
In my opinion, DMR, D-Star, and Yaesu System Fusion, you still do need to use the phonetic alphabet to differentiate between the letter Sierra and the letter Foxtrot. I don't think you need to do that anymore with RAID version 1. Okay? However, in the past couple months, they've also been working on RAID version 2. You ready to hear that side-by-side comparison? Here is RAID version 2. Listen up, this is brand new. It is not actually released in software yet. Stand by one.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
You guys ready to hear some awesome news about this? Still 6 kilohertz worth of speech input. Your output bandwidth for RAID version 1 is 1.5 kilohertz. That's 4-to-1 transmission. You're bringing a 6 kilohertz signal, not just chopping off the top and sending 3 kilohertz like SSB does. You're actually compressing the full 6 kilohertz input down to 1.5 kilohertz output. So if you put the same 5 watts into that narrower bandwidth, it's going to fly farther. Yeah? That means you can fit 2 carriers side by side in the same space that you would ordinarily send a single sideband signal. Okay? How's my sales pitch so far? Get this. It's free. This is all open source. You can download FreeDV and run this on your computer right now. You have to figure out how to plumb the audio from your microphone into your computer, into your radio. That gives some people fits, but you can do it right now. We've done over-the-air testing with this.
You have to find someone else.
They've made that easier, actually. They have a basically like an online. It will connect to the internet to find out who's transmitting when and where and what their grid square is and all that kind of stuff. So you can find people to test with. That's a nice feature of the FreeDV software. Let me finish up the sales pitch real quick. RAID version 2 compresses all 6 kilohertz worth of speech bandwidth into not 1.5 kilohertz, 1 kilohertz. So now you can fit 3 voice carriers into the same bandwidth that you are accustomed to using for single sideband. Would you like to hear these voice samples with that are actually over the air with noise floor included? Okay, if you got time for me, I'll play it. Here is single sideband at about -5 dB. You guys know what that's going to sound like, right? This is a hot mess. You can hear the human voice in there, yes? It's there. You can't make it out at -5 dB. You can hear there's a human in there, but it's just, sorry, not in log, right? Okay, here's what RAID version 1 sounds like at -5 dB signal to noise.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
You can hear some artifacting in there, right? It's not perfectly clear. You might need to use the phonetic alphabet to make yourself understood, right? But still, night and day difference, right? You ready to hear RAID version 2? -5 decibels.
G8S EZ test. Testing G8S EZ test 1, 2, 3, 4, 5.
Okay, so here's my thing. You've heard my sales pitch. You've heard the demonstrations. The bad news is that RAID version 2 is just finishing up their standardization process and bug testing and stuff like that. So you would have to compile software from source in order to use that today. And I'm not somebody who can test usefully and give them, real useful feedback. So it'll probably be a couple more months till we can download that software. But this is in hot and heavy development. And to be honest with you, once this gets implemented, I would like to do a lot of over-the-air testing with it. And I would love, love, love to beg ICOM, Kenwood, and Yaesu to include that in their HTs for the next generation. That's my personal thought. It does work today over HF, and it should work just fine over 2 meters, 70 centimeters, all that kind of stuff. So that's what I'm really looking forward to in the future. Thank you.
Who's next down there? You're up. If you can introduce yourself.
Yeah. All right, so I'm Elijah, Ka0ELI. My interesting thing today is my latest investment of a Motorola XPR 7550E, which is a nice little business model radio by a price point. But but by the powers vested in me through eBay and money, I now possess this beautiful little piece of technology that allows its big thing is DMR. So as we just were speaking about all the digital voice modes, we've got all sorts of these DMR repeaters throughout the state of Colorado, pre-programmed in here. So that's all I've got there. It is used, so it's showing a few signs of age, but for the price I got it for versus what you'd get it for new, I think it's pretty nice, besides the fact that it's the Motorola's favorite completely unstandard accessory connector on the side. Besides that, I have no issues with it, and from what little use I've really had with it, it seems to work very well. So that's all I've got for today.
Thank you. Okay.
Monty Rathman, Ka0MR. I just thought I'd bring an antenna here. It's a little, for 2 meter. It's a little unusual. In January of 2019, ARRL had a article on this. They have guys that are putting, or gals putting little kits together. And so this little cube antenna is what they call a slot cube antenna. It's vertically polarized, and it is full quieting. Some of you heard me, Steve, you heard me the other day, a few weeks ago on the radio on TechNet Night, and we were using this. It's extremely quiet. It's a little over 2 SWR, so for 2 meter. And what else can I tell you about it? Well, it's just a really neat little antenna. It's great for throwing in the car if you're going camping. You don't have to worry about breaking anything. You can just throw it in there and away you go and stick it in a tree when you get camping. But I keep it at home too. I put it up in the attic and use it. It's much better than my J-poles. Full quieting. It's better than any of the J-poles I have. So anyway, if you want to get the article, I brought the article from the January 2019. Yep, 2019. That's it. Thank you. I've never seen it in.
Don't get sick.
I'm actually going to share here to so you won't have to hold that. Let's see if this works. Okay, and let's see if I can. I'm just going to have to go with my cursor. Why is it so small? What if I do this? Nope, doesn't do anything. Okay. All right. Well, I guess we're going to go with something small. So my name is Roger Oakey. When I was when I was down at, of course, I've lost it here. There we go. So I and a number of people were down at DSES tracking Orion, and we had a computer failure partway through the 10 days that Orion was going out to the moon and coming back. And it got me kind of thinking about the equipment we have down there. And I wanted to understand what, how we actually controlled our dish. And so one of the things I decided to do is to see if I could actually create a controller for our dish, and with a long-term goal of improving it. But of course, the first step is to duplicate the functionality we have there. So, so this is kind of what I ended up with. If I'm going to zoom in a little bit here, some of you may have heard of the Arduino Uno Q. Which is a very interesting Arduino board in that it has a microcomputer on it that runs Debian Linux, as well as an Arduino supported chip, which gives you all the typical Arduino outputs. So not only can you handle, say, network traffic, but you can have a real-time operating system and write your code so it can react and stay on top of the movement of physical hardware. One of the problems that writing things in for Linux or Raspberry Pi or something like that is that it is a multi-threaded environment, and things may get busy elsewhere and start ignoring your hardware. So that's the advantage of actually having a Arduino that is paying attention to your hardware in real time. So the heart of it is this Uno Q, and the way that we control our dish is that we actually have 2 lines that go up to the dish that are, let's see if I can shrink this, that our azimuth is run with a minus 10 volt to plus 10 volt analog signal that tells it whether to go clockwise or counterclockwise and how fast. And our elevation is run from a negative, or from a 0 to a positive 10 volt signal. And so again, what I'm doing here is kind of duplicating the hardware that we have with a little bit more error checking, because one of the problems we had is that our dish was running in the wrong direction, and it was everything indicated on the panel that was running in the correct direction, but it was running in the wrong direction. So what I realized is the software wasn't looking at the encoders and throwing an error if it was running in the wrong direction. So I started off by putting a lot of checking in here and not redundancy, but the hardware self-checking. So these relays, the relays that are there right now are single pole double throw relays, which are just open and close relays, and all of these are double pole double throws. So it's running the open close side, but the other pole is actually feeding back to the Arduino, and it makes sure that if I close the relay, that the relay is actually closing, and if I open the relay, that the relay is actually opening. So so this is shrink. So to simulate the encoders that we have on our axes, we've got the elevation and the azimuth encoder, and these are the DACs that actually generate the this would be the elevation, so it's 0 to 10 volts. This is minus 10 to plus 10 volts. And this will actually connect to what's called a Jones plug, which is our interface in our control room up to the pedestal that actually runs the dish. So I know that this isn't directly applicable to amateur radio, but we do moon mounts occasionally, and so it would be used for that. So I'll use that as the excuse for presenting this. But this is something that's just been occupying my time for about the last month and a half. Is building this. Yeah, go ahead.
Do you have to run that output into servo amps then? And if so, how much juice are you feeding to actually do the drive?
Okay, so the question was, is this actually running into servo amps, or I'll say motor controllers? We actually have a Allen Bradley motor controller, and what's the other motor controller? Do you remember? Copley. It's a Copley motor controllers. So those are the ones that step up. The Allen Bradley is actually running a 480 volt motor, and the Copley is running a 240 volt motor. And this is actually one of the long-term goals, and that's why I kind of want to work the problems out here with the existing system, is that we're hoping to eventually replace the Allen Bradley with another Copley and the 480 volt motor with a duplicate motor that we're running for the azimuth. So we have two motors that are the same and two motor controllers that are the same. So all we need is one spare of each in the long run. Plus, what we'll do at that point in time is we'll start running the instead of this analog -10 to +10 and all these signals, is we'll actually start using the CAN bus or an RS-232 interface to drive the motors in the correct directions and at the correct speeds, which will pretty much get rid of everything you see down here in the lower left. It'll leave pretty much just the Arduino Q with a couple USB to RS-232 connectors, period, on it, or a CAN chip to run those. So we would simplify things quite a bit. I'm hoping to run it actually over, be able to run over a Wi-Fi or a hardwired network, and the interface is going to be to tell it the azimuth and the elevation to move the dish. For those that are used to optical photography, it's very important you accurately track the sky with a clock drive. Not so with radio astronomy. With radio astronomy, you have a 1 pixel camera. Since we have one antenna, it's only receiving one signal. So we use what one of our folks in the organization calls bang bang positioning. We let the thing drift off till it's about 3 dB down, and then we move the whole dish to a new position that's 3 dB down, but it leads it, so it then drifts into 0 dB down and then across to minus dB down. So the antenna actually stays stationary for quite a bit of time and then moves, because there's an awful lot of wear and tear on taking the brakes off and starting the motors up and all of that. So we try to move the dish as little as possible while we're tracking. So that's your esoteric presentation for the evening.
I think that's the last presentation. Thanks for all the show and tellers. If you have any interest, you can stop by and look at any of the devices if they haven't been packed up yet. And yeah, thanks everybody for coming out. Appreciate it.